So what were some of the lessons that we learned? And in fact, we'll apply those to the CPU interconnect in a slide or two. Well, one was that if you do voltage steps on a wire, you'll discover that if you don't worry about these impedance discontinuities, your signals, to use the technical term, turn to shit. Okay? So here's a nice signal, that the way you sort of thought it would look like when you designed your electronics. So here's a guy trying to put these pulses on the wire. Here's what it looks like if you pay no attention to the fact that you just run the wire, you listen to it somewhere in the middle, you don't worry about what happens at the end, the wire just stops. And all the energy of the transmission reflects off the end, and you get these horrible looking signals where all this is happening because of the reflection of this pulse off the end of the wire. And in fact, when it reflects, it inverts. And so we get these big upward going pulses, which are basically the echoes of the downward going pulse. So imagine if you had to communicate across a big canyon and it was echoing all the time. What would happen is soon that your voice, your message of 3 words ago would suddenly interact with the message, the thing you're trying to yell at the second as the echoes come back. That's exactly the problem that was here. And people began to realize that if I'm transmitting information across a certain distance, and I'll say what that certain distance is, I actually have to worry about these things. When things were slow, this never was an issue. Wires seemed very equipotential. When things got fast, and in fact, if I'm trying to make the voltage change, say, in 10 picoseconds from 0 to 1 volt, okay, if I have a wire that's longer than the distance light travels in 1 picosecond, then termination turns out to be, the wire is no longer equipotential. Okay, we have all these sort of impedance problems we have to worry about. And nowadays, people put every line on your PC board is an impedance-controlled trace. There's special electronics that deal with terminating it correctly, and that's essential to basically get very, very high-speed communication. And believe it or not, you have all the little communications channels that are actually connecting together the components on your chip are running at certainly, 5 or 6 gigahertz for sure, but on modern systems maybe up to 10 gigahertz. These are very high-speed transmissions that are happening. Okay, well, let's think for a moment. If I were actually going to say, okay, I buy the religion, Chris, how should I organize this? Well, the best thing I can do is to use differential mode signaling, okay, where I actually use 2 wires, and the receiver receives by measuring the difference in the voltage between the 2 wires. And that's as compared to a single-ended signaling, where I only use 1 wire. So why are 2 wires better than 1? What is going on there that would cause you to say, as an engineer, why would you prefer 2 wires than 1? I heard a voice, but it wasn't quite loud enough for me to... Yeah? Right, so the advantage of this so-called differential signaling is that you get a very good, what's called common mode rejection. Something that would affect a single wire will in fact affect both wires pretty much the same. And in fact, you tend to engineer this so that anything that's happening happens to both wires. So you do twisted pair, or you do something fancy with a PC trace to make sure, they experience sort of this, they sample the surrounding noise in pretty much the same way. And the advantage of that is I don't care what happens to the wires as, together, because I'm only listening to the difference between them. So we have this notion of differential signaling as solving a whole class of problems that single-ended signaling doesn't. So that's a huge step forward. The other thing that's nice about this, if you think about if we're putting current in 1 wire to charge it up, we're taking current out of the other wire to discharge it. So in fact, in some sense, the same amount of current is flowing, right? We're just determining where it's going. Whereas down here, as we turn currents on and off, there's actually switching noise associated with the turning, going from connecting to one power supply to the other. Whereas here that we're drawing pretty much a constant amount of current and just deciding which wire it goes into. Down here, we're turning it on and off. And turning it on and off creates its own noise problems. The traditional backplane, where the wire is passive, this is very slow, okay? Think about the impedance that I see driving into this thing. So I have a characteristics impedance of the wire. Well, I see sort of in the middle, I see that going off on both sides. And in fact, that halves the effective impedance at this driver here. Which is to say that you carefully designed a 50 ohm trace and a 50 ohm driver, but when you start driving the 50 ohm trace in the middle, you suddenly see 25 ohm characteristic impedance, and now the driver's sort of going, whoa, I can't put enough current in the wire to do the right thing. So all your voltage steps are half of what you think they're going to be, and the whole thing, it turns out this was just problematic from the start, and the more people understood about the E&M, the more they realized the problems. And then if I switch from this driver driving to that driver driving, in the clean world, you can say, well, what difference does it make? He was putting on a 0, now this guy is putting on a 0. But it turned out there were big glitches as the current was being sourced and sunk, are those words, in different places. So lots of interesting electrical problems.